Welcome to this problem-solving session. Today, we'll be tackling LeetCode problem number 2135, count words obtained after adding a letter. This problem challenges us to think creatively about string manipulation and efficient data structures. Let's dive in and explore how we can solve it step by step. In this problem, you are given two string arrays called start words and target words. Each string in both arrays consists of lowercase English letters, and none of these strings contain duplicate letters. The goal is to determine how many strings in target words can be obtained by adding exactly one letter to some string in start words and then rearranging the letters of the new string in any order. Importantly, when adding a letter to a string in start words, it must not result in duplicate letters because all the strings are required to have unique characters. Once all the valid transformations are identified, you need to return the total number of valid strings in target words that meet this condition. The output for this problem must be an integer that represents the count of valid transformations. Now, let's look at an example to better understand the requirements. Suppose start words is ant, act, tac, and target words is tac, act, acts. The output is 2. Here's why. For the string tac in target words, we can add the letter k to act in start words and rearrange the result to form tac, making it valid. Similarly, for act, we can add the letter t to act and rearrange the result to form act, which is also valid. However, for acts, no string in start words can be modified to meet the requirement, so it is not valid. This gives us a total of 2 valid strings. In another example, if start words is BC, ABC, and target words is ABC, ca, cab, ABCD, the output is 1. Here, ABC, ca, and cab in target words cannot be formed by adding a single letter to any string in start words. Even though rearrangement is allowed, they don't meet the requirement of adding exactly one new letter. However, for ABCD, we can add the letter D to ABC in start words, forming ABCD after rearranging. This makes it valid. So, the total valid strings in this case is 1. Now consider the case where start words is B, C, and target words is B, C, C, A, B, C. The output here is 0. None of the strings in target words can be formed by adding a single letter to any string in start words and then rearranging the result. This is because every string in target words either requires more than one letter to be added or cannot be derived from any string in start words at all. Therefore, there are no valid strings in this example. To summarize, the total count of valid strings in the last example is 0. The problem also imposes certain constraints. Both start words and target words can have up to 100 strings, and each string can be up to 26 characters long. All strings consist solely of lowercase English letters, and no string contains duplicate letters. When solving this problem, you should also consider edge cases, such as single-character strings in both arrays, scenarios where the arrays are at their maximum size, and cases where no transformations are possible. It's also important to handle strings in target words that are already present in start words since they do not involve adding a new letter and therefore should not be counted as valid. To solve LeetCode problem number 2135, we need to figure out how many words in the target words list can be derived from the words in start words by adding exactly one letter and possibly rearranging the characters. The first approach we considered is the brute force method. In this approach, for every word in start words, we try adding all possible letters from A to Z at every position, generating all permutations of the resulting word. Then, we check if any of these permutations match a word in target words. While this approach is conceptually straightforward, it's computationally expensive. Generating all permutations for a word introduces a factorial term, and when combined with the size of the target words list, the complexity becomes infeasible for larger inputs. This inefficiency, along with redundant computations, makes the brute force approach impractical despite its simplicity. A more efficient method is the optimized approach using sets. Instead of generating permutations, we represent words as character sets. Here's how it works. For each word in start words, we create a signature, which can either be a sorted string of its characters or a bit mask. Then, we systematically add one character at a time and check if the resulting signature matches any word in target words. To make lookups efficient, we pre-process the signatures of all target words and store them in a set. This allows us to check for matches in constant time. The complexity of this method is significantly reduced. Pre-computing the signatures for target words involves sorting, and iterating through start words while adding one letter requires manageable operations. This approach avoids redundant computations and leverages fast set operations, but it does require careful implementation to ensure the signatures are consistent and accurate. To make the solution even more efficient, we can use bitmask optimization. In this method, each word is represented as a bitmask where each bit corresponds to a specific letter. For example, the word ABC would be represented as a bitmask where the first, second, and third bits are set to 1, resulting in the value 0111. Adding a letter is as simple as flipping the corresponding bit in the bitmask. Here's how this works in practice. We convert each word in target words into a bitmask and store these in a set. For each word in start words, we calculate its bitmask, flip one bit at a time to simulate adding a character, and check if the new bitmask exists in the target words set. This approach is extremely fast because bitwise operations are highly efficient, and it minimizes memory usage by avoiding the need to store or sort strings. However, it does require a solid understanding of bitwise operations to implement correctly. The chosen strategy for this problem is the bitmask optimization approach. Representing words as bitmasks is particularly effective because it reduces the character addition step to simple bit manipulations. This eliminates the need for sorting or generating permutations, which can be computationally expensive. There are a few key insights that make this approach ideal. First, the order of characters in a word doesn't matter, only the set of characters does. By using bitmasks, we efficiently represent these sets. Second, adding a character is equivalent to flipping a bit, and checking for matches in the target word set is extremely fast thanks to the O(1) lookup time provided by sets. The efficiency of this method, with a complexity of n times 26 plus m times k, makes it highly scalable for larger datasets. While the implementation does require careful handling of bitwise operations to avoid bugs, the benefits in performance and memory usage make this trade-off worthwhile. In conclusion, the bitmask-based strategy is the most optimal solution for this problem. It offers speed, memory efficiency, and scalability, making it well-suited for handling large inputs. By leveraging the power of bitwise operations, we transform the problem into a series of efficient computations, avoiding the pitfalls of sorting or generating permutations. While this approach demands a solid understanding of bitwise manipulation, its advantages in performance far outweigh the complexity of implementation. This makes the bitmask method not only the fastest but also the most elegant solution to the problem. In this problem, we need to determine how many words from the target words list can be derived by adding exactly one letter to any word in the start words list, and then rearranging the letters. The solution involves breaking the process into a series of clear steps. First, we normalize the input words. By sorting the characters of each word, we ensure that any rearrangements are treated equivalently. For example, the words ABC and cab both normalize to ABC, making it easier to compare them. Next, we encode these words as bitmasks, where each letter corresponds to a specific bit in a 26-bit integer. For instance, the word ABC is represented by a bitmask where the first 3 bits are set to 1, simplifying letter-based operations. This encoding is not just compact but also lays the foundation for efficient word transformations later in the algorithm. To proceed, we store the bitmasks of all start words into a hash set. The hash set enables us to perform O(1) lookups, which is key to maintaining efficiency as we process the target words. Now, for each word in target words, we calculate its bitmask representation. We then simulate the removal of each letter, one at a time, by turning off the corresponding bit in the bitmask. Since there are 26 possible letters, we perform up to 26 such transformations for each word. For each modified bitmask, we check if it exists in the hash set of start words. If it does, it means that adding the removed letter to a word from start words can produce the current target word. Each successful match increments our count, which ultimately gives us the number of derivable words. This approach works so well due to several key insights. First, normalization through sorting ensures that we treat all rearrangements of a word as identical, simplifying comparisons. Second, the bitmask representation is both space-efficient and allows for quick transformations, such as adding or removing letters. Third, iterating through all 26 possible single-letter removals guarantees that we test every valid transformation of the target words. Finally, using a hash set for storing start words bit masks ensures constant time lookups on average, making the algorithm scalable even for larger inputs. As for the data structures, the hash set is pivotal for its fast membership checks, while the bitmask integers provide a compact and efficient way to represent and manipulate character sets. Now let's analyze the complexity of this solution. The pre-processing step, which involves normalizing and converting the start words to bitmasks, has a time complexity of n*m, where n is the number of start words and m is the average length of each word. The space complexity here is n, as the hash set stores the bit masks. For the target words, processing each word involves creating its bit mask and testing up to 26 transformations. This gives a time complexity of t*m, where t is the number of target words. The space complexity for this step is t, as we only process one word at a time. Finally, the solution handles edge cases such as words with duplicate letters, words that have no valid transformations, and even empty input arrays, ensuring robustness across different scenarios. The solution begins by creating a set of sorted character representations of all words in the start words list. Sorting the characters of each word ensures that we have a consistent way to compare words regardless of their original character order. This set, start_set, allows for 1 average lookup times. Next, we initialize a counter count to 0. This counter will keep track of how many words in the target words list can be derived by adding a letter to a word from start words and rearranging the characters. We then iterate over each word in target words. For each word, we sort its characters to create a consistent representation, sorted_word. This ensures that we can systematically check if removing one character results in a word that exists in start_set. Inside the loop, we iterate through each character in sorted_word. For each character, we simulate removing it by constructing a new string, candidate, which excludes the current character. We then check if this candidate exists in start_set. If it does, it means that the word from target words can indeed be derived from a word in start words by adding exactly one letter. In this case, we increment the count by 1 and break out of the inner loop to avoid double counting. Finally, after processing all words in target words, we return the count. This value represents the total number of words in target words that can be obtained by adding a letter to a word in start words and rearranging the characters. The algorithm is efficient due to its use of sets for quick lookups and its avoidance of unnecessary computations. The outer loop processes each word in target words, and the inner loop iterates through the characters of each word, making the solution scalable for the given problem constraints. Here, we begin by importing the necessary packages and defining our solution class and its word count method. The method takes two string arrays, start words and target words, as input. First, we create a hash set called startSet to store sorted character representations of all the words in start words. This ensures that we can efficiently check for matches later. By iterating over each word in start words, we convert it into a character array, sort the array alphabetically, and then convert it back into a string before adding it to the set. This pre-processing step allows us to standardize the word representations, which is key for the comparison logic we'll use shortly. After this setup, we initialize a variable count to 0, which will eventually hold the number of words in target words that meet the required condition. Next, we start iterating over each word in target words. For each word, we again convert it into a character array, sort the characters, and create a string representation called sortedWord. This step ensures that the word is in the same standardized form as the words in startSet, enabling an apples-to-apples comparison. We are now ready to check if removing one character from sortedWord can result in a word that exists in startSet. To perform this check, we use an inner loop that iterates through each character in sortedWord. By removing the character at the current index, we form a new string called candidate. This is done by concatenating the substring before the character and the substring after the character. We then check if this candidate exists in startSet. If it does, it means that by adding just one letter to a word from start words, we can form the current word in target words. In such a case, we increment the count variable and break out of the inner loop, since we only need one match per target word. Once all words in target words have been processed, we return the final value of count, which represents the total number of target words that can be formed by adding a single letter to any word from start words. This concludes our implementation, demonstrating an efficient way to solve the problem using sorting, hashing, and string manipulation. To begin solving this problem, we first pre-process the start words list by converting each word into its sorted character representation. Sorting ensures that we can compare words regardless of the order of their letters. For example, the word ant remains ant, cat becomes act, and bat becomes abt. Once we've converted all the words, we store these sorted strings in a set called start_set. This set allows us to perform quick membership checks later in the solution. So, at this stage, start_set contains the elements ant, act, and abt. Now, we process the target words list to determine how many words can be formed by adding exactly one letter to any word in start words. First, we initialize a counter, count, to 0. For the word bats, we sort it into abst. Then, we systematically remove each letter, one at a time, to form new candidates, bst, ast, and abt. Among these, abt exists in start_set, so we increment count by 1. Similarly, for cats, sorted as axt, we try removing letters to generate candidates. When we remove s, we get act, which is in start_set, so we increment count again. For ants, sorted as anst, none of the candidates like nst, ast, or ans match, so we move forward without increasing the count. At this point, count stands at 2. After processing all the target words in the first example, the final value of count is 2, meaning 2 words from target words can be formed by adding one letter to a word in start words. Now, let's consider the next example where no matches are found. In this case, the start words are dog and frog. Sorting these gives Joe and Fgor, which we store in start_set as Joe, Fgor. This pre-processing step ensures that we're ready to efficiently check matches when processing the target words list. In this example, we process the target words list, which contains dogs and frogs. For dogs, we sort it into Joes and then remove each letter in turn to form candidates like Goes, Dos, Degius, and Joe. However, none of these candidates are found in start_set. Similarly, for frogs, sorted as Fgors, we generate candidates like Gors, Goes, and Fgor. Again, none of these match the entries in start_set. Since no matches are found after processing all target words, the final count remains at 0. In the final example, we work with start words that include a ub and abc. Sorting these gives us a ub and abc, which we store in start_set as a ub abc. This setup allows us to handle target words efficiently as we attempt to identify words that can be formed by adding just one letter to these start words. Here, we process the target words list, starting with ABCD, which, when sorted, becomes ABCD. By removing one letter at a time, we generate candidates like BCD, ACD, ABD, and ABC. Among these, ABC exists in start_set, so we increment count to 1. Next, for ABC, sorted as ABC, we create candidates like BC, AC, and AB. Here, AB is found in start_set, so we increment count again. After processing all words, the final count is 2, indicating that 2 words from target words can be formed by adding one letter to a word in start words. Let's begin by analyzing the time complexity of the solution step by step. First, we consider the processing of the start words list into a start_set. Each word in start words is sorted, and sorting a word of average length k takes k*log k time. If there are m words in start words, we repeat this operation m times, leading to a total cost of m*k*log k. Next, we process the target words. For each word in target words, sorting it costs k*log k, and for each character in the sorted word, we generate a new candidate string by removing that character. This generation step costs k, and checking if the candidate exists in the start_set is an O1 operation because sets provide constant time lookup. Since there are k characters in the word, the inner loop costs k squared. With n words in target words, the overall cost for processing them becomes n*k*log k plus k squared. Now, combining the two steps, the total time complexity is the sum of processing start words and target words. This gives us m*k*log k plus n*k k asterisk log k plus k squared. Simplifying this expression, the overall time complexity of the solution becomes O m asterisk k asterisk log k plus n asterisk k asterisk log k plus k squared. Shifting to space complexity, the major contributor is the start underscore set that stores sorted representations of all words and start words. The space required for this structure is proportional to the total number of characters in start words, which is O m asterisk k. Additionally, while sorting a word or generating candidate strings, auxiliary space of O k is used temporarily, but these variables are reused and do not scale with input size. Therefore, the overall space complexity is dominated by start underscore set storage, which is O m asterisk k. Let's compare this optimized solution to a brute force approach. A naive method would involve generating all possible strings of length k1 for every word in start words and comparing each of these strings to every word in target words. Generating transformations for each word grows exponentially with k, resulting in a time complexity of approximately O m times k times 2 to the power of k plus n times k. By contrast, the current solution uses sorting and set lookups to achieve a much more efficient time complexity of O m asterisk k asterisk log k plus n asterisk k asterisk log k plus k squared. This makes the optimized approach significantly faster, particularly for larger input sizes, as the exponential nature of the brute force method would quickly become infeasible. Analyzing the best, worst, and average case scenarios provides additional insight into the behavior of the algorithm. In the best case, none of the words in target words can be formed by adding a letter to words in start words. Here, the inner loop breaks immediately for each word in target words, and the time complexity simplifies to O m asterisk k asterisk log k plus n asterisk k asterisk log k, as sorting each word remains mandatory. The worst case occurs when every word in target words requires checking all k candidates before finding a match. This results in the full complexity of O m asterisk k asterisk log k plus n asterisk k asterisk log k plus k squared. On average, some words in target words will match earlier in the inner loop, which reduces the number of checks. However, the asymptotic complexity remains the same as the worst case due to the dominance of the k-squared term in the inner loop. Finally, let's solidify our understanding with a mathematical proof of the big O complexity. Sorting words is the dominant operation for both start words and target words. For start words, sorting all words costs O m asterisk k asterisk log k. For target words, sorting and generating candidates contribute O n asterisk k asterisk log k plus k squared. Combining these terms leads to the overall time complexity of O m asterisk k asterisk log k plus n asterisk k asterisk log k plus k squared. On the space complexity side, the primary factor is the storage required for the start underscore set, which is proportional to the total number of characters in start words, resulting in O m asterisk k. Therefore, the space complexity is linear with respect to the input size, while the time complexity balances sorting and candidate generation effectively. One of the most common mistakes in this problem is ignoring the requirement to add exactly one letter. For example, some solutions might inadvertently allow multiple letter additions or simply rearrange the letters of start words to form target words. This goes against the problem constraints. To fix this, ensure your logic explicitly handles the addition of just one letter and then validates the result. Another frequent issue is inefficient string comparison. Sorting strings or checking permutations to compare them can become computationally expensive, especially with larger inputs. A better alternative is to use more efficient techniques, such as bit masking or hashing, to represent strings. Additionally, neglecting duplicate entries can lead to inaccurate counts, so it's important to pre-process your input using sets to remove duplicates. Finally, overlooking edge cases, such as empty input arrays, maximum string lengths, or target words that cannot be formed, can cause your solution to fail. Thoroughly testing these scenarios is crucial for a robust solution. Inefficiently searching through target words is another common pitfall. If you naively iterate over all possibilities for each word, it can result in timeouts on larger datasets. A better approach is to pre-process start words into a hash set, allowing you to check membership in constant time. From an interview perspective, this problem highlights the importance of adding one character and working with permutations. Representing strings in efficient ways, such as bit masking or frequency counts, is a key takeaway. Bit masking, in particular, is powerful here because the alphabet size is fixed at 26, making it both space and time efficient. When optimizing, it's useful to explain why bit masking is superior to sorting, especially for large datasets. Finally, don't forget to discuss edge cases, like empty input arrays, non-overlapping start words and target words, and single-character strings. These demonstrate your ability to think critically about problem constraints. This problem shares similarities with several other LeetCode problems that you might encounter. For example, LeetCode 242, Valid Anagram, focuses on comparing character frequencies, which is directly relevant here. LeetCode 49, Group Anagrams, emphasizes grouping strings based on their character counts, which involves similar pre-processing techniques. LeetCode 1347, Minimum Number of Steps to Make Two Strings Anagram, deals with transforming one string into another, highlighting the importance of understanding character-level transformations. Lastly, LeetCode 1178, Number of Valid Words for Each Puzzle, is a great example of utilizing bit masking for efficient comparisons. When considering alternative approaches, sorting strings is the most straightforward. This involves sorting the characters of each word, but it has a downside. The time complexity is relatively high at O, n asterisk m log m, where n is the number of words and m is the average word length. It's simple to implement, but it doesn't scale well with large datasets. On the other hand, character frequency arrays improve comparison speed by representing each word as an array of size 26, where each index corresponds to a letter's frequency. This is faster than sorting but uses more memory, making it less efficient than bit masking. Bit masking stands out as the most efficient approach for this problem. By representing each word as a 26-bit integer where each bit corresponds to the presence or absence of a specific letter, you can perform comparisons and set operations extremely quickly. For instance, adding one letter is as simple as flipping a bit, and checking membership becomes a fast operation. This method is highly optimized for both time and space when compared to sorting or frequency arrays. However, it does require a solid understanding of bitwise operations, which might present a learning curve. The trade-off here is clear. While it's the optimal solution in terms of performance, it may take extra effort to understand and implement correctly. Mastering this technique is not only beneficial for this problem but also for other problems that involve fixed-size alphabets or sets, making it a valuable tool in your problem-solving toolkit. Great job following along. To summarize, we used hash sets and string manipulation to efficiently solve this problem. Remember to practice similar problems to master these concepts. Thanks for watching, and be sure to check out more coding solutions to sharpen your skills. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!